let's do what we can. So you see this colorful objects, right?
Pretty colors.
Yes, I like it. I was doing it while pretending that I'm listening to the federal agency and waiting for you. So here is the diagram, learning diagram of this course, right? We started from free space evolution operator, right? And then we took different models and different methods, theories. So up to last time we were drawing this thing, most advanced was density harmonic oscillator, because we introduced weather operators, coherent states, and we were focusing on this commutation. Go back. Okay, commutation, right? Then I was not bringing this little table for a few weeks, and meanwhile we went through two-dimensional rotator, three-dimensional rotator, and hydrogen atom, right? What was interesting in the rotators, that same as in the harmonic oscillator, we were dealing with commutation of key operators. Maybe I do not blame you if you have zero memories about it. We have so short course. Typically, this subject is like quantum theory split over a year, because it's only an overview is squeezed into half a year. But this is like a connection. And now we are going to jump to the next step to find another system where commutation plays significant role. Why this commutation is needed? We had commutation of operators, and we had Heisenberg equation of motion. Remember, I was bragging of being a descendant. Now we will have Heisenberg equation of motion for the spin. So you see, it has connection to previous subjects. What else? Weather operators. We had weather operators for the harmonic oscillator. There will be weather operators for spin. What else? Yeah, I think it is enough of connections, right? I'm going to keep wasting time and show a couple of slides from previous lectures. I will try to do it like instantaneously quick, hoping that it will just flash back and you memorize all of them, or at least it will spark some of your memories. But realistically, probably only jokes and fun figures will be memorized. Okay.
Quick question. So if you are an academic descendant of Heisenberg,
I need
then,
to be humble. I need to stop recording.
well, my question is, are we also academic descendants of him
No.
because we're your student?
No, because I'm a fish younger.
Right.
I
But
think undergrad barely counts.
well,
Research on your faculty.
nephews. Better?
Yeah.
Okay, so harmonic oscillator, right? You can jump lower than the yes, basement. For Sam taught us that distance cross product times p is angular momentum. And yeah, this way, cross product by this determinants, right? And then if you formulate it as quantum operators, you can have rotation in different angles. And these quantum operators, if one processes it carefully, will follow an absolutely beautiful commutation relations. When you rotate along x and y forwards, then along y and x, it will be equivalent to rotation along z. And if you ever were drawing molecular models, like three-dimensional objects and rotating, you know that just making a couple of rotations in one direction may induce rotation in the other. So this is something that we kind of skip, but it is one of another cornerstone of quantum theory. And when people derive in details three-dimensional rotators and Bayesian models, it is inevitable part. Maybe if you go to next level, you go through just little heads up. So similar things like angular momentum, X, Y, and Z direction will be projected onto the spin. Another concept of people who drink too much and do not wash their heads and speak offensive language. Yes.
Yeah.
That's how
Whatever.
I got.
It's like a melody that fell out.
So see, degeneracy. You see this little thing.
No,
So that's fine, but I do.
What?
So angular momentum and then degeneracy. Like if it rotates very few, no rotation. S orbital, it is not degenerate. P orbital is 3 degenerate, D orbital is 5 degenerate. Okay.
Mhm.
I wonder how does it connect to spin?
It's one up and one down for each
So,
one.
right?
Yeah.
So it will be somewhere in between 1 and 3, right? I was going to keep the intrigue for 20 minutes, but Melody already answered it.
and then it's gonna be between 1 and 5 and then 1 and 7. But it has to be,
If you want to devote your life to lanthanides and actinides,
no.
you would have a lot of these things. You can learn spectral terms where one add together several spins, angular and spin momentum, and then you shouldn't ask about.
Alright. All right, I'll stick to my organic.
Another concept that we didn't take, but it doesn't mean that it doesn't exist. Selection rules. So spectral transitions between some orbitals are allowed and between another orbitals are forbidden. And you will hear about it. Maybe Fred has already heard about it in inorganic.
Occupation of levels.
Selection rules. So if you want to give hard time to your advisors, each of you can try and ask, what do you think about selection rules? And see how they will answer. I'm sure they all are aware of it, but you hear some like independent second opinion. I promise, all of them know what to answer. But if you do it different way, then we can gather here and share their answers and compare. Selection rules. Maybe homework. Ask your advisor about selection rules. Because we do not have time in the class. For this. Okay, few more background foundations. Because of the commutation, one can practice Heisenberg equation of motion, right? For expectation value of operators, we did it for harmonic oscillator, right? So the expectation value of creation operator and the incubation operator accumulate phase. This is also an interesting observation. You will see how beautiful it is projected and almost repeated for the spin. Right? So there will be creation and incubation operators for the spin, and they will also rotate. Okay. And then if one combines creation and incubation operators for oscillator, one gets position or momentum if one subtracts, right? If one combines creation and incubation operators for spin, one would get magnetic field projections. Okay. And magnetic field projections do what? What's the right word? Precession.
Precession.
Yes. Yes.
Because they have a certain tab.
So even if Eva didn't do EPR experiment yet, she will before graduating. Therefore, probably she knows nature about the precession. So basically, the primary clients of this sequence of 2 lectures are those who love NMR and EPR. Okay. We will read this. Here are your parameters to scan, right? And here is the creation operator for the spin. We need to get that read. Okay, maybe I can humbly focus camera on not myself, but on the screen, so that it's better. On with it. Forward. Yes. What do you see?
MRI.
Yes, can you please explain what it is
Oh,
Magnetic resonance imaging.
and how to like think about it? What is it? Huh?
I don't really know
So-
specifically what it's used for opposed to like other types of brain scans, but you're looking at something inside one's head.
So, what is this big donut?
So that's,
magnet?
Yes.
Yeah.
So, is there like constant magnet or something is rotating?
well, it's probably rotating.
To focus on different areas. in
Yeah.
space.
So here's what my thoughts are on this is that like it has a magnetic field and it goes through the brain or whatever part of the body, and does that like disrupt the signal in a way that like we can measure and then project as an image?
So it is automated NMR experiment that focuses on different areas of the brain. Right? So if you are practicing NMR, then you have this as well. So for NMR, you have 2 fields, one constant field that splits energies of spin or angular momentum states, and then transversal field that radio frequency field that induces transition between them. And then one can focus them on different areas and then rotate this focus so that one scans everything. Okay. I don't know if the answer is sufficient, but at least it helps us to help our train to depart in the right direction.
So cool.
Oh,
I'm mesmerized.
So- right word for magnetism. What is here? What do you see?
Like spinning, there's a spinning magnet. Well, it's kind of 2, but like one I think is kind of
This
disturbing
looks
before it is the other.
like those diagrams for the homo and lumo.
What is different for this spinning magnets of left and right?
They're spinning opposite direction. No. Yeah.
And this
opposite direction.
cheap GIF figure is not ideal, but yeah, spinning in different direction. So this one takes any direction from top to bottom, left to right, and this one performs like little deviation from the axis. That's not good. Actual. Right? So, and what are these little red things with labeled as N and S?
North and south.
Sober. North and south of what?
Poles.
Yeah, pole,
Oh,
magnetic poles.
Pole magnet, strong.
oh,
Right?
yeah.
So here there is no magnet, here is magnet. So in presence of external magnet, little needle of a compass will be oriented, and even if we let it rotate freely, it will rotate not freely, but by a little deviations from the main direction. So if one looks on the spin as a little magnet, when, according to Melvin, when there is no external magnet, they'll spin up and spin down at GGM, right? State. If one increases magnetic field, their energy, one gets smaller, another gets bigger, right? So it is the energies of spin up and spin down state as a function of external magnetic field. And it's called by the name of the person who discovered it, starting with letter Z. Means huh?
Z.
Z, like
I saw it, I remember. seeing it.
Jason Momoa is Aquaman, right?
Yes.
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 Demon.
Yes, so man from the ocean, from the sea. In German, it is instead of C,
See,
it is Z.
Oh,
Zeeman,
okay.
right? So it is Zeeman effect. I should put here the photo of Jason Momoa. Then you would memorize it. So, one of the goals or standard practices of physical chemistry and sciences is to translate what we see and observe in real world into mathematical equations and to human words and vectors in all three directions. Since here we do not have any instruments, then we skip real world and we just translate from equations to words and from words to equations. Or from equations to equations. So this absolutely. So if you want to be theorist of a spin, well, to be theorist of one spin is maybe will be not competitive, but if you're a theorist of two spins, you can still publish papers. But if you want to do theories of it, or just go through like educational courses, one needs to use the same things as we did for everything in the quantum world. We need wave functions
Okay.
and operations. Okay, so when we were speaking about free space, boxes, oscillators, in rotations, it was possible to develop continuous wave function that depends on continuous variable, right? And then as a bonus, we were also doing expansion coefficients, eigenstates, vectors, right? So quantum state can be represented as a set of expansion coefficients as a vector. For spin, it is hard to imagine what is the actual continuous wave function. Therefore, people just abandon continuous wave function and speak only in the space of expansion coefficients.
okay.
Since there are only two states, up and down, there could be each quantum state consists of only two expansion coefficients. Like and their absolute value squared added together should be equal one. Okay? So it will be very beautiful for Dirac notation and for matrix notation. So if we want to practice Dirac notation, then we can call spin up will be alpha, spin up will be beta. And if you want to, so it is like two directions on the axis, on two dimensions.
Theta spin down.
I
Or is it
never
so
remember.
they're-
For all my years, I always mix them. You figure it out yourself. Do not catch me saying it wrong. Yeah, I will fail. I know it's 50% of failure, but I will pick the wrong one if you ask me.
So one is
Alpha
spin
is
up and
up.
the other is spin down.
Yes, and then if you want to convert it into vectors, the 1, 0 is, let's say, up, 0, 1 is spin down. And then there will be operators to, well, if I show this slide and just explain everything, then we will be done. I have another like 40 slides and we will arrive to this thing in whatever minutes. But wave functions, right, and operators that can be expressed either in matrix form or Dirac form. It is something like the language of
The language,
quantum mechanics of spin, quantum theory of spin.
okay.
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 And we will have Heisenberg equation of motion operators. Those are already letter operators. See, plus and minus, up and down, converting from maybe beta is up, alpha and down. Then it will go down, and this will go up.
Yeah.
So, what is shown on the slide, and did anyone saw such ugly writing before?
Yes.
Thank you. Did you see any equation that looked this way before? In which circumstances?
Well, I guess which circle equation am I, or is it?
Well, circle is explained in the second line. First line shows M is vector as a summation of S sub I. So guess what is S?
Spin.
Spin. What is M?
Magnetism?
Magnetization. Like magnetization of a sample. So if one add together all spins, one can get
You get NMR.
right, and one can, if you have transition metal, like iron most popular, with unpaired spins, and you put several atoms together, these spins will add together and will become a massive magnet, right? So magnetism is a summation of all spins, and spins in these abstract things, they just one half, and magnetism has units. So what is the proportionality factor between abstract spin and real world magnetization? So if one goes to Wikipedia, that some of your school teachers advise you not to read, but either they know much more than is shown in Wikipedia, or they fear competition with it. I know less than Wikipedia, I don't fear competition, so it's only a help. So this mu sub b, I remember when we were in the
Really struggling with it.
we were struggling with A sub B,
Yeah.
and B was standing
Both
for both. But now B is different.
It's for, is it for the magnetic Bohr?
Yes, it's for Bohr. Mu sub B is Bohr magneton, and it is nothing but proportional coefficient between spin and magnetization. And if we admit atomic units, which I strongly encourage, and probably you are not resisting of doing, all of you are doing projects using atomic units, right? Then it's so much better than this 10 to the minus blah blah blah, right? So you see benefit of using atomic units in any practical things. What do you see here?
Ball. It's a magnetic field. It's a block sphere.
Yes.
Guess that.
Yes. Your glory is recorded. Camera is focused on you.
No.
But can you describe what you see without any background? This background is good, but even without, just how do you interpret what is shown? Like you already told that it is a sphere, right? Which is a scientific word for ball. Yeah. And are there any labels?
There's I and mu and the arrows.
So north and south pole and S. Never saw. How they labels here?
Like up and down,
Yeah.
and like in a cat. Is that a cat?
That's a cat.
Yeah. Yes. Dmitry +1, I taught you well. Thank you, Emma. I see fruits of this class. Yes. But how to interpret that, like, if I am a little pedestrian, with a walking cane, and right now I put my flag on the North Pole. What does it mean? Yeah, I should draw better. And it is ugly face. Just whatever, please. No, it looks more like a cockroach. But if this object is on the North Pole, how do you interpret it in terms of spin quantum
Spin
state?
is up.
Yes.
It's all positive.
Okay. And if this beautiful cockroach-like pedestrian walks to the South Pole, what can?
Down.
Kill him.
Okay. So it is in the spin down state.
Sure.
And we were just recently telling that it is too degenerate, right? Only,
Yes.
only two spin states, up and down.
There's a side spin state.
And yes, now what is side spin state? Like if it is neither up nor
Is
down.
it like a midpoint between?
Well, see how many midpoints are.
Lot infinite.
Yes. And tell evaluate what they like. What do you think about that? Can we be like 50% up, 50% down is clear.
Yes, but so it could be a ratio of.
Right.
Oh,
And if you want to sound scientific, or you are scientific, but if you want to confirm
the sum of the two spins has to equal 1 or 100.
yes, but this instead of ratio, if the quantum state is contributed by several basis states, what's the right scientific word?
Wait, say that one more time.
If a quantum state is a summation of two bases, I guess.
Superposition.
Yes, so
Ah,
superpositional state.
melody plus one.
No, that's right. So ratio, superposition, right? Superpositional state of a spin. You are progressing well and through this complicated material. So by the end of the Monday meeting, I want to arrive to this slide.
Okay. Haven't we already gotten to it?
No. I can
No, we
explain.
haven't gone through all that math
I
yet.
can explain what is there, but in the ideal world, after doing this class, you can be hired to national lab and derive these equations yourself.
I'd like to spend a little bit more time in your lab first. You know, get the fundamentals. finalized, and, you know.
Okay, so.
Well, I mean, if I get my.
It'll
Hey,
work
guys.
out.
So,
Later.
what is shown here? What is shown here and where we want to arrive by end of Monday meeting?
Spin state.
X,
Super-
Y, and Z.
Yes, so instead of the basis where we say up and down, we need to introduce X, Y, and Z projection, right? So we need conversion.
Vectors.
Right. And then we need to connect this block sphere with quantum superposition, this, as you call ratio states, and magnetic projections. And this is doable. This we could do it like right away today, but we need to introduce Heisenberg equation of motion for spin projection. So 10 minutes about.
What then?
So Heisenberg equation of motion for this who we were doing Heisenberg equation of motion in harmonic oscillator. No, shouldn't be the competitor of Heisenberg. So instead of playing like everyone looks and watches, it means it's terribly boring. Operators or expectation values operators.
Okay.
So and now we will have spin operators. creation and annihilation of a spin, right? Or magnetic spin operators. And when we solve Heisenberg equation function and compose these solutions, we will get projections of magnetization. That is a vector connecting center of a globe with a equator on any point of this globe, and the trajectory. So when we had a harmonic oscillator, like mass on a spring, it was just forward, backward with momentum, right? You remember this?
Yes.
Sorry,
you zoned out?
I was off in La La Land for a minute.
Okay, and what is our goal in this spin business is to see how magnetization, this Bloch vector on the Bloch sphere, will rotate. So we need to obtain a solution for rotating Bloch vector. And getting math of it will mount wings behind your shoulders to become experts in NMR. Okay? So now let's describe what do you see on this figure.
So basically, once it hits 90 degrees is when the states kind of start to expand. And then once it hits 180, it flips and then they all converge.
Perfect. Yes. How does it connect to EPR and NMR experiment?
Is this so that like, as like it's rotating, like you get like the entire, like you can scan your entire molecule?
When no, it goes with this individual experiment shows to only one/1/2 spin. If it is NMR, it will be proton spin of proton rather
Yep,
than electron.
no, you're right.
Many arrows correspond to many samples, many protons, and each of them has its own direction of magnetization. When they come together, it means they come to the same value and together and give strong signal. What are these 90 and 180 degrees? So when we will finish our Monday story, we will see how spin rotates on equatorial plane. And it will rotate freely without any intervention. But if one applies radio frequency resonant field, it will go from north to south and back, right? So two opposite directions, equatorial travel and north to pole, polar express. Okay? So 90 and 180 degrees are parameters. Like when this line goes up, it means someone is applying radio frequency wave. If it is 0, nothing is applied. And here 180. So it goes for longer duration. And then they come coherently backwards. So this superposition in the inhomogeneous ensemble is a key for spin echo, photon echo, and NMR and EPR. Just snapshots. Okay. Really, you want to go so deep? Really? Okay. As class should know, I think it's I want to deliver in the remaining few minutes a little simpler. Oh yes, this is good. So nowadays, everyone is welcome to comment on this little equation. What do you see here? Probably this is
Shapes in common.
this is main equation of today. Well, only this equation doesn't give us all things, but it is like foundation, major cornerstone.
No, I'm just tired.
Yeah,
So we have I will screw it up by naming it wrongly, but like alpha is down, beta is up, and C sub alpha C sub beta are proportions, right? In the way that C alpha squared plus C beta squared will be nearly 1, right? So we are on the sphere.
So is it basically, it's kind of like dealing with sines and cosines?
Yeah, they can deal like saying yes, good analogy.
is-
And here is the wave function. The wave function is represented just by superposition of two base states.
you already answered my question.
Okay.
Wait, just to make sure, the psi is the wave function,
Yes,
or
wave function of spin, of single spin.
if it's in that, the cat, like that, is that like an eigenstate? Is that like a so basically like the overall spin is described by like the combination of the positive and negative spins, like their individual contributions.
Eigenstates.
Yeah. Okay,
Okay.
so those on the right are the eigenstates.
Mhm.
Okay, all right. Makes sense, kind of.
And now, the people who drink too much and do not wash their hands and speak offensive language. So,
I just stay up.
Then you're
No, why would I admit to not washing my hands?
That's shallow.
not. But really, what?
so
Hey, I know many respectable people that.
angular,
Okay.
angular momentum 0, no degeneracy. Angular momentum 1, p orbitals 3. And now we know two states. What will be the angular momentum of spin between 0 and 1? Yes. It's my beautiful too. Okay. And the language is like singlet, doublet, triplet. Triplet because triplet degenerate, doublet because doublet degenerate. Okay, ready? Now let's go to Dirac.
What?
Right.
Dirac notation. Dirac notation. So we agreed, and Fred confirmed that wave function is a superposition of up and down with different expansion coefficients. Now I'm replacing up and down by these basis vectors. If you do not want to believe me, it is my task to convince that vectors with 1 in along x and then with 1 along y will be orthogonal to each other. So if you want to represent two orthogonal basis vectors, it is a good idea to use this 1, 0 and 0, 1. Right? If we practice scalar product, if we multiply them, row by column, you'll get 0. That's the mathematical orthogonal. Okay. So those two basis vectors are good representations for like down and up spins. So mathematically, one can work with matrices and vectors. Some crazy books and teachers start quantum theory from spin. It looks a little unorthodox, but mathematically it is the simplest problem. And one can develop a lot of math. And then particles in the box and the oscillator will, so simple. Okay. Alpha, beta. Where do we see spin in our freshman chemistry? When we have 4 quantum numbers: principal, orbital, magnetic, and spin. Okay. Do not say in public that it is a rotating sphere, although you can think it inside yourself. Alternative names: up, down, plus, minus, 0, 1, alpha, beta.
Alpha is down.
Probably, but I would not take quiz on it because I would fail it myself. Now, if we want to switch from down to up, we need to design, like, operators are composed as bra times ket. Vectors like instead of row by column, we formulate it as column times row. Yes.
Are you still in that training?
Yeah.
Oh, yes.
It ends.
So, how to convert spin on the everyday language is a continuous problem for anyone who tries to teach similar course. If you ever teach it, you'll face the same challenge.
Okay.
So we need to identify two states of an object. So spin is not up and down, is not like there are so many up spins, so many down spins. It is the state of the same object. So object is a human. A human can like to wake up early or wake up way.
Yeah.
On all and scalar. And a cup of coffee or some magic, some wizard can convert an all to a scalar. Okay,
Yeah.
you're getting a concept of spin.
Yeah.
Yeah, you get it. Now let's put it into math. So here is a cat of the all. Here is your cup of coffee or wizard that converts it into scalar. Okay,
Yeah.
states, Dirac states, and operators. So if one convolute mathematically an all with an all, it will be one. It's identical to itself. Scalar product gives one. If one convolutes scalar with scalar, it will be one. If one convolutes an all with scalar, it will be zero. Scalar product is zero, right? Now, if we make a dyadic product, swap the order, and all will change, we will not change the all, but will not affect the scalar. You will like get zero to scalar. This one is an actual operator, how to convert an all into scalar. We need dyadic product of the cat and bra of these things. And now how it works. So if this magician cup of coffee, if it is the operator acting on the cat, and here is the cat and bra. First, we can look on it as this box is an operator, this box is a wave function, but we can reset our thinking. This box is a wave function, and this box is a scalar product. This scalar product, as we proved a minute ago, will be one. So we get a scalar. So same things with the spin. So if we have this alpha and beta acting on alpha, it will reproduce alpha. Okay, I think it is enough for today. Have a fun weekend. Let me know if any help is needed to stop share so that your hands are. No, we need to focus on doing this. Yes. Yeah, meeting is done. Have a nice weekend.